Today I'm going to show you a major procedure in analytic chemistry. Titrations are used to determine the concentration of an unknown solution. First I'm gonna proceed a strong acid-base reaction for demonstration. In this clip I'm titrating HCl with a sodium hydroxide solution. Add the solution dropwise until our indicator, in my case universal indicator, turns to the color indicating the equivalent point. It would be better to use something like phenolphthalein, but I used universal one for the video. I collected the pH values as well as the used volume and created this chart. As you can see, the pH raises quite slowly, until it suddenly shoots up. This is expected for a strong acid-base reaction. To determine the concentration, let's take a look at the reaction equation. As this is a 1-to-1 ratio, at the equivalent point the concentration of HCl equals the sodium hydroxide concentration. At a pH of 7 I used 10.8 mL of 0.5 molar sodium hydroxide solution. That means I've used 5.4 millimoles sodium hydroxide to neutralize the same amount of HCl, dividing the amount of substance with the used volume. In this case I've used 1 milliliter of HCl, the concentration can then easily be determined. Now let's take a look at another example. In this clip I'm titrating acetic acid again with sodium hydroxide solution. As you may know, acetic acid is a weak acid, means it's not fully dissociated. As you see, the starting pH is bigger than the HCl one. Again I've collected the data creating this chart. As you can see, the pH raises at the beginning faster but slows down approaching the equivalent point. This is expected due to the buffer solution effect. A buffer solution is a mixture of a weak acid and its conjugate base. In this case acetic acid and sodium acetate. This slows down the neutralization. First, let's calculate where our equivalent point should be. For this we need the base constant and the negative logarithm of the acetate ion concentration. Dividing by 2 brings us to the hydroxide concentration, which can then be subtracted from 14 to get the pH. Again we can calculate the concentration of the unknown solution with quick math. Now I want to show you another example of a titration, but this time not a acid-base one. Instead I'm going to determine the concentration of my hydrogen peroxide. For this iodometry is used. First I am gonna add 3 grams of hydrogen peroxide to an volumetric flask and fill it up to 250 mL. Then 20 mL are added to an Erlenmeyer and same volume of 1 molar sulfuric acid are added. This is filled up to 100 mL. Then 1 gram of potassium iodide is added and the color change should occur. In acidic nature hydrogen peroxide oxidizes potassium iodide to iodine, which colors the solution dark purple. Then a 0.1 molar sodium thiosulfate solution is prepared and added dropwise to the iodine solution. The iodine will be reduced as shown. When the titration comes to an end, it may be hard to see the iodine color. For this a small amount of starch solution can be added. Starch reacts with already tiny amounts of iodine forming in dark blue complex. The titration is then continued to colorless. To calculate the concentration of H2O2 we first set up the stoichiometric relation. For every mole of sodium thiosulfate 2 moles of hydrogen peroxide are expected. You could also say that 1 milliliter of sodium thiosulfate corresponds to 1.7 mg of hydrogen peroxide. Dividing this by my sample weight brings us to a weight percentage of 41.7%. To assure my outcome was right I quickly checked for density. As you see, my density of 1 milliliter hydrogen peroxide is about 1.164 grams per cubic centimeter. In an online chart it can be seen that this corresponds to a weight percentage of about 42.5.